Good morning, everyone. It is 11 a.m. on the West Coast, and we're going to get started with part 4 of our Using ANSYS Solutions to Help Improve Electronics Reliability, Comprehensive Multiphysics. My name is Glenn Compton, and I am joined later in this presentation by one of our application engineers, Adam Ramel. So electronic systems are found in nearly all industries, and ensuring these systems remain operational and perform their intended function in a variety of environments is critical to product success and customer satisfaction. Companies who properly address electronics reliability concerns through simulation can meet many of the objectives stated here. Traditionally, companies have used a design, build, test, break, and then fix design cycle. As I'm sure you know, this approach can be expensive and time-consuming. The design rules and best practices associated with this process may not provide engineers with enough guidance to properly design modern, cutting-edge products. By using simulation, virtual prototypes can be created and tested virtually. This provides engineers with a higher degree of confidence that the eventual physical tests they do run will be successful. Performance, safety, and cost are all critical considerations in the design of electronic systems. Devices are required to reliably perform their intended function in a wide variety of demanding environments. If electronic systems get too hot or have a mechanical failure, they may not be able to perform their intended function. In some instances, this could put people at risk. A wide range of customers have benefited from ANSYS electronics reliability solutions. Benefits typically include reduced design development and material costs, reduced product development timelines, and improved product performance and reliability. ANSYS provides a suite of tools and workflow solutions that address a wide range of electronics reliability concerns. Each simulation tool set plays a key role in the understanding of how electronic systems operate and perform in a variety of applications. Over the last 3 weeks, we've discussed signal and power integrity, thermal reliability, and mechanical reliability as separate focuses. Today, we will discuss the importance and practice of coupling all of these physics together for improved reliability and product performance. First, let's review these independent focuses. Printed circuit boards, ICs, and IC packages are used in almost all electronic products across all industries. With electronics getting smaller, engineers need to design boards that are smaller than ever and incorporate all the required features. Accurate modeling and simulation of these components are key to reliable end products. Electrical simulations help address concerns related to signal and power integrity, EMI, EMC, and others. Maintaining thermal integrity is an essential part of designing best-in-class electronic systems. Thermal simulations allow engineers to evaluate and optimize cooling strategies and component designs. Using ANSYS tools, users can evaluate thermal performance from the chip die level all the way up to the system data center level. Users can also consider downstream effects such as thermal mechanical effects resulting in PCB and package warpage and stress. Being physical structures, PCBs and other electronic components are susceptible to failure due to excessive warpage, shock, vibration, drop, and other environmental conditions. Structural integrity needs to be maintained to help ensure electronic devices perform their intended function. ANSYS has a wide variety of solutions for quickly preparing high-fidelity simulation models that can be used to assess the mechanical performance of electronic systems. Bringing it all together, it is important not only to categorize the electrical behavior of an electronic system, but also the thermal effects that arise from its operation and potential environment. In turn, the deformations in the structure itself, potentially serving as the cause of mechanical failure in PCBs, packages, solder interconnects, and other structural components. Therefore, when simulating electronic systems, it is important to consider the problem holistically by considering these various multiphysics effects. To explore this holistic approach, I introduce Adam Ramel.
All right, thank you, Glenn. Just start sharing my screen. There we go. Okay, so as Glenn mentioned, we're going to be talking about multiphysics today. Now, there's certainly a lot of interesting simulations you can do that you can learn a lot from, where you don't necessarily need to take a multiphysics approach. You can start with just a single physics. But that being said, certainly once you start doing a more complex type of simulation, such as a electronics reliability, then to get a really good holistic picture of everything that's going on, you need to go into a multiphysics type simulation. So these are all of the This is kind of a workflow that ANSYS uses for an incomplete electronics reliability simulation. So you certainly don't need to do all of these. You can do just a couple of these or just part of this, but we're going to go through kind of the entire suite of tools and processes today, so you get a whole holistic idea of what to do. So starting with ANSYS Sherlock on the left, you will start pre-processing your simulation in Sherlock. It's a very well-developed preprocessor with lots of very good and well-developed capabilities. Kind of one of its star capabilities is its parts library, which includes over 1 million unique parts. So if you're looking to model a specific electronics component, there's a good chance that that component's already in the Sherlock library, which definitely speeds up and makes it a lot easier on you when you're trying to run that simulation or set that simulation up. So from there, kind of in parallel, you will be running an electrical simulation using HFSS or a power and signal integrity simulation using SI wave. From those electromagnetic simulations, you'll develop a Joule heating loss map for your electrical components. That Joule heating loss map goes into ANSYS IcePack, which is ANSYS's thermal solver and CFD solver. So from there, it will take that power heat loss map and turn it into a temperature field on your model, which you can then pass into ANSYS Mechanical, where you can run any sort of mechanical and structural analysis of your model. This usually involves like the thermal stress simulation, but it can also include shock and vibration analysis. So for example, like a PSD analysis and those sorts of things. And then finally, you can take kind of all of those simulations and all of those inputs and take it into ANSYS Sherlock, where you can run a reliability physics analysis. There we go. So now the question is kind of what can we run these simulations on? And the basic answer to that is just almost anything electronics related. So you can do basically all scales of electronic components. So you can run anything from the chip and die level. We can go up to an IC package, a board assembly, backplane assembly, system level, all the way up to a server room essentially. And there's a way basically in order to kind of build from one level to the next, ANSYS has developed a reduced order model or a ROM that will help you to run a server room level simulation and allow you to include kind of details all the way down to the chip and die level. And I'll be talking about the ROMs in a little bit later. So as kind of an overview of the multiphysics capabilities, these are all of those tools kind of again as how they communicate with each other. So again, on the electromagnetic side, we have HFSS, Maxwell, and Q3D. Those are kind of our general purpose electromagnetic solvers. Then on a PCB level electromagnetic solver, there's SI wave. For chip level simulations, there's Red Hawk. And then for structural, we have mechanical. For reliability, we have Sherlock. And for system and ROMs, there's ANSYS Twin Builder. And kind of at the heart of all of those is ANSYS IcePack. And ANSYS did this because thermal issues, I guess, are the main problem when it comes to electronics reliability concerns. All of the issues really stem from the heat being generated while these components are in use. And so because of that, ANSYS IcePack has become kind of the crux tool, I guess, of all of these different tools. So all of them can communicate with IcePack, and IcePack can communicate back with all of the other tools. And we'll see how this benefits us in just a moment. So for one example of that, if we're looking at a chip package, since it's a chip package, we'd be using ANSYS Red Hawk to generate what's known as the chip thermal model. And this is basically the temperature-dependent power and layer density information of a chip. So once you've developed this chip thermal model in ANSYS Red Hawk, you can import that data into IcePack, where it will run the CFD and thermal analysis, and then it can send that information file back to ANSYS Red Hawk for electromigration reliability analysis on that chip package. So for electro-thermal analyses, in general, the problem is, again, the heat being generated in electronics components while they're in use. Now, our goals as engineers is to be able to mitigate and design for those thermal effects to prevent them from doing any damage and to increase the performance of our electrical components. The only way to really be able to do that, though, is to be able to, or is first, I should say, we need to be able to understand where that heat's being generated, how it's being distributed throughout our model, et cetera, before we can even start to design some thermal mitigation measures to compensate for that. And of course, the best way to be able to understand the thermal behavior of our model is using ANSYS tools. So as I mentioned, there's a few ANSYS electromagnetic tools, HFSS, Maxwell, Q3D, SI Wave, et cetera, and all of those kind of work with ANSYS IcePack in that they can send information back and forth to each other. So for example, after you've done your electromagnetic simulation, you can send that information to ANSYS IcePack, where ANSYS IcePack will then run the thermal analysis and determine the temperature at which your model is operating at. ANSYS IcePack can then send that information back to the electromagnetic solver, where it can run the simulation again, changing the material properties based on the information from IcePack. So just kind of giving you I'll go into that in a little more detail and giving you a specific example of that. Here we have a chip package system. So normally, if this is just kind of a one-way coupling, meaning it's just going from electromagnetic to IcePack and to the thermal analysis, the assumption there is that your electronics components don't change temperature, potentially both in space and time, meaning that you have a constant temperature of in this case, your chip package system. Maybe it's room temperature, and you just assume everything's room temperature and run the analysis in that way. But that's a pretty big assumption, and you're losing a lot of information, a lot of accuracy when you do that. So using this coupling, you run the electromagnetic simulation, develop that power map, send that to IcePack. IcePack then runs the thermal analysis on it to develop the temperature profile within your component. And then it sends that temperature map back to the electromagnetic solver, which then solves again by first updating the material properties of your entire model based on the temperature profile from IcePack. So this kind of two-way coupling that goes back and forth really helps to increase the simulation accuracy by updating the temperature both spatially and in time too. Of course, if you're running a transient simulation, these things may be heating up at different rates and those sorts of things. So this coupling can really help improve your accuracy of your simulations. So adding in the mechanical portion of this. So first you'll run the electrothermal portion of it, as we just discussed, where you will run your electrical analysis, send that in, run the thermal analysis in IcePack. And then based on those results, you probably have some design criteria. Like for example, there's probably some maximum temperature that you're trying to not exceed. And if your design currently is exceeding that temperature, then you'll need to go and make some design changes to your model and then rerun it. And this becomes kind of an iterative process. And I'll talk about that in just a minute on a good way to make that much more efficient. But for now, it just becomes an iterative process that you do over and over again until you reach that design goal. And then once you've reached that design goal, you can then take that solution and take it into mechanical, where again, then you can run things like thermal stress and, like I mentioned, shock and vibration analysis and those sorts of things. So once it's been in mechanical, you can look at the deformation of different portions of your model. So we can look at the entire PCB. We can look at just the solder balls, seeing the stresses in the solder balls. Maybe those are starting to break. And then we can also do something referred to as submodeling, where essentially if we want to look at, like, this is a specific portion of your BGA. So essentially you run a coarse model, maybe modeling all of your entire BGA as maybe a single solid body, and essentially get the boundary conditions for a small portion of your BGA. Then you can run a much finer model with where you model a lot more details and get a lot more information out of it using this submodeling technique. So going back to that iterative process of kind of redesigning your model and then until you meet some design goal and then moving on from there. But that becomes a very manual process that can be very time consuming. One way to avoid that is using optimization tools. And the other question is that even once you've designed, say you've designed a heat sink that did get your maximum temperature down below your design goal, that's great and you can just move on from there. But there's always a question of, well, maybe there was a slightly better, slightly different designed heat sink that would have improved the performance even better. And you may never know that. And so the answer to that is optimization. And so on the right here is kind of the workflow for the optimization. So number one is you set up your model. So in this case, we've designed our heat sink, our initial design of the heat sink. And then step two is you define your DOE or your design of experiments. So maybe you want OptiSlang to change the number of fins or the size of the fins in terms of their length or width or thickness or whatever the case may be. And you can set up all of those different variables that you want it to try with some parameter or some limits on each one, right? So the number of fins could be between 5 and 20, for example. And then what OptiSlang does, well, actually, and then you just hit run and it runs through the rest of the process automatically. But what OptiSlang does and what it gives you at the end of the simulation is it runs the simulation many times. And the first thing it does is called a sensitivity analysis, where it takes each of those variables that you gave it and it changes each one independently and determines what effect that had on the simulation. So maybe changing the number of fins only had a 2% change in the maximum temperature on your model, but changing the length of the fins had a 30% change in the maximum temperature on your model. So in that case, it knows that the maximum temperature is determined much more by the length of the fins than the number. And so it uses that to really intelligently figure out what design iterations to run before figuring out what the most, or I should say the set of most optimal designs are. And so at the end, what you end up with is the kind of the graph in step 4, where each dot there represents a different design iteration that it tried. And usually you end up with kind of a curve in the bottom left of the most optimal designs. And that's just a trade-off between the variables that you were looking at. So I mentioned maximum temperature, but maybe you're also interested in reducing, say, the mass of your component. And so you may have multi-variable goals there. And so there's a trade-off between those two. But either way, OptiSlang is a great tool for showing you the most optimal designs and helping you pick one of those. Okay, so going back to the ROMs a little bit. So I mentioned modeling like a data server room down to everything down to a chip level model. Now, it would be near impossible to run a simulation on an entire data server room, modeling everything down to those finest of details. The problem there is really the compute power. Maybe in 100 years we'll have desktop computers that can run simulations like that, but in the meantime, ANSYS has come up with something referred to as reduced order models or ROMs. And what these do is, we can take this as an example where we have a PCB on the bottom left here, and what they did is they ran several ice pack simulations on it by inputting a power generation for the components and looking at the temperature as a result of that. And they reduced and they iterated on the amount of power generation in the PCB many times and ran the simulation several times, getting different temperature profiles each time, of course. They then took those kind of compilation of results, input them into the ROM builder, and that exported, and that, I should say, spit out the reduced order model. You're then able to take that reduced order model and put that in the higher level simulation. And that way, it is a very accurate way of representing the fine details in a model without actually needing to model them in all of their detail. Okay, so as a summary, the benefits of multiphysics. The number one benefit is certainly simulation accuracy. And this is just because in a complex simulations like electronics reliability, the ability to model multiple physics is pretty essential to really understanding the problem as a whole. The next advantage here is being able to optimize your design by looking at the relationship between the design input and the output. This is using tools like OptiSling to be able to optimize your designs so you end up with the best design possible, giving you the best performance possible. And finally, we can model multi-domain systems using ROMs, which significantly help the solution times as well as the accuracy without needing to model down to very fine details. All right, and with that, if there are any questions, I will take those now. All right, if not, I will turn it back over to Glenn.
Okay, thank you, Adam. So this morning we've talked about the combination of using a number of ANSYS products together to solve the comprehensive multiphysics approach of all these challenges. You can use ANSYS Space Claim for cleaning up your models, ANSYS Mechanical for things like drop, ANSYS IcePack certainly for the thermal applications, ANSYS SI Wave and HFSS for understanding power integrity and whether or not you have any magnetic issues that could be contributing to the heat problem. Next week, we'll be looking at ANSYS Sherlock and what we call reliability physics analysis. Now, modeled correctly, any of these solutions can become extremely complex. Ozone Engineering is here to help. In addition to providing and supporting ANSYS solutions, we also offer consulting services with specific experience in FEA, CFD, and high and low frequency electromagnetics, where they're here to help you get the answers you need through ANSYS simulation modeling. If you have any questions about today's session, please feel free to reach out to us either by email, telephone, or through our website. Thank you for attending, and please remember to register for next week's session on reliability physics analysis. Thank you very much.